This is 11.3, which is about direct and inverse variations. The objectives for this lesson are as jotted down below. They're going to be for you to be able to recognize relationships as inverse, direct, or possibly neither. Some just do not fit these two different types of models, so you're going to need to recognize these two models when they do occur, because they do happen in our everyday life all the time. Also, we're going to be applying these to science problems. When you watch the 11.1 video, remember we do have this overall project that we're aiming towards, where we're going to be calculating a focus point, and that is going to deal with some sort of inverse variation. So you're going to need to make sure that you understand this 11.3 lesson. To start this lesson, I want you to focus on two visuals just to get us warmed up. So this first visual are these three circles, and what I want you to realize is that as we're moving along, I'm going to focus on the radius and the circumference of these circles. So here's our radius, it's from the center to the edge, and then the circumference is the length all the way around. Center to the edge, the circumference is all the way around. Center to the edge, all the way around this bigger circle. The relationship between the radius and the circumference are directly related. They're directly proportional. As you get larger in terms of the radius, as this radius is going up, it's getting bigger and bigger, so is the circumference. Okay, so something really interesting happens with this relationship that we're going to be seeing in a little bit. The other thing is something that's not so direct. So here I have what I'm going to call oil drums, or these containers for oil. And this first container, this cylinder shape, is going to be something that's kind of skinny. So we're going to be looking at the width, or the diameter of the base of these oil drums. And we're going to also be looking then at the height that the oil reaches in these containers. So what you're going to notice is this cylinder, if we widened it, then the oil is going to have, it's the same height and everything, but the height is going, the cylinder is the same height, but the height of the oil is not going to fill the top anymore because you're expanding the width of this drum. Same thing here. If you got the width of the base is larger, what's happening to the height of the oil, it's getting smaller. It's basically not as large. This is related, but this is what we call an inverse relationship, because what's going on here is as the width is getting larger, the height is essentially doing the opposite of what the width was doing. So they are doing the inverse of each other. So this would be an example of an inverse relationship. This could be a very interesting study because the height of this oil has everything to do with the pressure of the flow that's going to be coming out of this oil drum. So it might be a good thing of study if you're some sort of engineer looking at, I don't want this flow to be too overpowering, so I don't want the pressure to be too much. So your height would be playing a factor, and therefore also the width of your base would be a factor in the design of your oil drum. With those visuals in mind, then, we're going to start our lesson. So finally, yes, you get to do some notes and vocabulary. So the first term of vocabulary is a direct variation. Oops, there's my... So this is box your vocab if you need to help you organize your notes. But the direct variation, what I basically want you to get out of this is that if you have these two variables, such as a radius and circumference, let's look at radius and circumference. They vary. So radius and circumference, let's say. And what happens is if you take the quotient of the two, what's going to happen is you're going to get some sort of constant number. If this happens, that throughout trials of experiments, or when you're looking at the circles, if you take your two variables, so your circumference divided by your radius, the circumference, this would be trial 2 or circle 2, divided by radius, trial 3, the circumference divided by the radius, and it happens that you get the same constant number every time you do this. What you call this is a direct variation. Okay, and just as a reminder, quotient is the result of division. So biggest thing about direct variation is the relationship between the two is linked by some sort of quotient being a constant. Oops, I didn't mean to cross that out. Okay, how your book had it. It was on page 656. They wrote it like this. So if x and y vary directly, then y divided by x is equal to some sort of constant k. Keep in mind we tend to write things in terms of y, or we write things with y being equal to something, so y in terms of x. So keep in mind that a lot of the time we like to solve for y. For example, when we were doing linear equations, we liked y equals mx plus b. When we were doing quadratics, we liked y equals ax squared plus bx plus c. We just like that y by itself. So keep in mind this is looking like a quotient. But if you lumped and got your x and y's together, so in this case all you would have to do is divide x from both sides, there you have that quotient again. So I mean these things are exactly the same. There's nothing different about these except for they rewrote the x on this side for this equation. So you got to be careful of that. But when you're looking at the x and y in terms of each other, so yeah, you get the x and y to one side of the equation. If it's a quotient of the two and they equal some sort of constant, you have a direct variation. Alright, so here's an example. This is actually, let's say the experiment here is looking at and measuring circles. So thinking of that visual, let's say we looked at the radius and then the circumference. So radius, x is the radius, y is the circumference, and we measured it to be ½ an inch. Okay, so the radius was ½ an inch. Therefore, there's a certain equation that links these together that would say then the circumference, or if you measured the circumference, it was about. Alright, so let's look at an example here of a direct relationship or a direct variation. Let's keep in mind that circle example, and let's look at two variables x and y. In our experiment, we're going to look at 4 different circles instead of 3, sorry, 4 different circles. And our experiment is to measure the radiuses, so we're going to let x stand for radius and y stand for circumference. So let's say we measured that first circle's radius and it was ½ an inch, or in other words 0.5 inches. Okay, and then you took a string, wrapped it around the circle. So you took a string, you wrapped it around the circle, you cut it off, and then you straightened it out and you measured how long that circumference was, so how long that distance around the circle was. And you measured that to be about 3 inches and 1/8, or in other words 3.125 inches. Alright, same thing in trial 2, you measure the radius, it's 1 inch, and then when you measure the circumference, it's 6 1/4 inches, or 6.25 inches. Same thing all here. Here is your measurement for radius. Here's your measurements for circumference. So you did this experiment, and what you found was something interesting. When you divided the circumference by the radius, you got approximately the same answer every time. Okay, this is what we call a constant. It's something that is happening constantly, and I'm going to say it's about 6.26, and this is what we would call a direct variation. Okay. I just want to point this out there. Had you had something for like this, for example, so in trial 1 you measured it to be 0.3 and then something was 1.2. You measured something to be 0.8 and it was 8.1. I don't know what would maybe fall under this category. Yeah, you could come up with the story behind this, but I'm not being creative right now. So what you would find though is when you took your y divided by x, and calculated it out in this fourth column, what you're seeing is these are all different. This is what you would identify as not constant, and so therefore this experiment would not, your two variables would not be directly related. Alright, I do just want to graph this really quickly. So this is that same chart that I took from here. Oh, there we go. So radius and circumference, we're pretending these were the radius measurements that we took. These were the circumference from our experiment. Okay, so here I'm going to go ahead and plot 0.5 and then go up about 3.125, so about right here. Okay, oops. All right, then we will go 1 and then up 6.25, so I'm going to go 2, 4, 6, and then 0.25. This would be 6, 8. So I don't want to go to 7. 7 would be right in the middle. I want to go like half of that. So here we go. 6 point, or no, a quarter of that. Oh, sorry. So there's about 6.25. Not the best plot. 2.75. So now I'm all the way over here. This would be 2.5. 2 and 7.75 would be about right there. And then all the way up to 17. Oh gosh. I'm just going to do this for being able to see where I need to plot. Alright, so 2.75 up to 17.25. So that would be right about here. Okay, once again, if you took careful time to plot these, this would be a little bit better. Here's my 4, and then we're going to go all the way up to 21. Okay, so here is what that graph looks like. What you're seeing is this looks like a straight line. And that's what direct variations do. They actually look like linear equations. And if you think back to what linear equations was, here is y equals, in this case if we let just b equals 0, here we have a y equals slope times x plus the y-intercept, which was 0. There we have that direct variation kind of model. If I go ahead and lump my x to both sides, what we would get is y over x is equal to some sort of slope. It's a direct variation. Okay. There's a lot of stories that could possibly go behind that. There's circumference. You could think of, for example, I don't know, the more time you give to somebody driving, the farther they'll go. I don't know, things like that. It's where as one thing goes up, as one variable goes up, the other one goes up as well. Okay, so now our next thing that we need to keep straight. Now we're going to move on to what is an inverse variation. So I'm going to box that. This is our second major vocab of this unit, or of this section. So now the big difference here I want you to note is product. Keep in mind product is now the result of multiplication. So you're going to multiply your two variables this time and then get a constant. So in your book they have the inverse variation models and definitions written once again on 656, and they have it written in this way. So if they vary inversely, your two variables, when multiplied, are going to be equal to a constant. So that's what they were demonstrating there. This is where it does become a little bit confusing, because if you were to solve for your y, like we'll tend to like to do, what you would do is divide x from both sides. You would divide x to both sides. What you're going to get is y equals k over x. And this now looks like a quotient. So this looking like a quotient can be a little bit confusing, because you think, oh, quotient, that's going to be a direct relationship. But keep in mind you want to lump your x and y together. See if when you lump them together it's a quotient or a product that you're looking at as equaling some sort of k. So again, I would write this example down. It's just a quick chart. Fill in some numbers here. So here my chart. If I looked at, this could be my x and this could be my y. If you go ahead, you had some sort of trial or experiment that you were running, and you measured this to be 0.2, this to be 81.6, this to be 0.8, this to be 21.5, and then so on through your trials. When you started looking at your data, you could say, well, let's check if this is an inverse relationship. So once again, an inverse relationship suggests that when you multiply those two variables throughout the experiments, do they have a relationship? Is there some sort of pattern going on when you multiply each one of those variables together? And you can see, yeah, it's not exactly alike, but still, because they're all right around the same realm, when you multiply, this is a constant. Oops, I'm sorry, this should be 17 or 16, I guess. averaging out, it's about 16.5. So this right here is direct. Oh, sorry, I copied and pasted. So this right here is an inverse relationship. Okay. So now this versus, all right, let's look at this data. All right, this is not some sort of constant, so this is not an inverse. All right, this is where you might want to check, okay, well, should we check if it is a direct relationship? Well, then you would want to start doing 122 divided by 0.3, 81 divided by 0.8, see if when you do that calculation, these all become the same. So if they don't, then it's neither. Okay, so it's potentially neither. So check the quotient, check the product. If the quotient works out, then that's going to be your direct. If the product works out, then it's going to be an inverse. If neither of them work out, then it's going to be neither of them. Alright, so I'm just going to quickly graph this inverse relationship that we found. So when we did our B and times A or A times B, we got the 16, and it doesn't matter for multiplication what order. So when we do these multiplication terms, what you're going to always get is 16. So I'm going to plot these points, 0.2 and 81.
What will this graph look like?
0.2,
Oh, what will it look like? Brady!
we're going to go all the way to 81, so right about here. Oops. Alright, 0.8, so it's getting closer to my 1, and then up to 21. So right about there. 2.75, so as my A or my independent variable is getting larger, what I want you to be seeing is just like in that oil drum case, that other variable, the one that we're linking, is getting smaller and smaller. So 3.32, 4, it's going to be something like that. When we draw a line connecting all these, if you wanted to, you could try to get some more data points if you were at a loss for the shape, but that is what an inverse relationship looks like when graphed.